Our next approximate method is the portal method. So if I have here a frame that's pinned at the bottom, it has a height of h and a width of L, and I load it with P, how is it going to deform? Something like this red line here, where I have slope but no deflection at the pins, of course, but with my fixed corners, I have this weird twisted shifting shape. And what we're going to find is approximately in the middle here, I have a point of inflection where I can assume zero moment. With this zero moment assumption, I can then draw a free body diagram of half of the frame where I have my reactions at the pin, force X and force Y, and then I have my internal forces along the girder of shear and normal, where moment is equal to zero. Similarly, if I have a fixed support, it's going to deform something like this, where again I have this swirl at the top here where I have zero moment, but with the fixed end, the moment is now zero towards the middle of the columns instead of at the bottom like the pin, because the moments resist rotation. So it's going to come up and then rotate. Meaning if I were to draw a free body diagram of this section, I would now look at half of the height to where my zero moment occurs, in addition to half of the width. So with these assumptions and approximations, my moment diagrams are going to look something like this, where we have magnitude-wise symmetry, where it goes up just as far as it goes over and then crosses zero in the middle. And for our pin supports, the moment diagram will be a triangle coming all the way down. For those columns, versus the fixed supports that are going to have that point of inflection in the middle. The zero moment locations are half of the work for the portal method. The other half of the work of the portal method is the internal shear for the columns. So if I've got a 2-bay frame that's fixed supported along the bottom, all I've drawn here is the top half of the free body diagram. So h divided by 2 because it's fixed. Then my shear on the outside columns is going to be 1V, where the shear for my inside column is going to be 2V. And that is the same even if I have multiple inside columns. So just for fun, I added one in here, and you know what? Let's just make it a little bit longer and pretend that it was pinned. It is still going to have 2V as the horizontal reaction. Putting this into practice, we have a frame here with 3 bays, 10 feet, 12 feet, and 8 feet wide from left to right, and the entire system is 10 feet tall. We've applied an 800-pound force at the left corner A. Find the moment diagram for A, B, C, D. Our moment diagram is going to have this triangular look to it based on the portal approximate method. So what I need to find are the magnitudes at the fixed ends A, B, and C, and then due to symmetry, that would be the negative portion of the moment diagram. To finish this diagram out, it is going to cross 0 at the center of the frame. Starting at half the height, I'm going to have shear A, 2 shear underneath B, 2 shear underneath C, and shear underneath D. Note that all the columns are supported by fixed ends on both ends, so that means that we've divided the height by half, 5 feet, for that point of inflection where moment is equal to 0. That does mean, ladies and gentlemen, that we also have normal forces here. Summing for forces in the x direction, I'm going to have my load minus v minus 2v minus 2v minus v, and I find that v is equal to 133 1/3 pounds. So that means my centers are double that at 266, and my outside v's are 133. Next, I'm going to take a free body diagram sectioning my girder in the center of each bay, where again, moment is equal to 0. Now I want to take my free body diagrams from 0 moment to 0 moment, in this case, center column and center beam, because then I don't have to mess with internal moment forces and connectors at the corners. I can just go straight to shear and normal, and it makes for an easier free body diagram. So starting with corner A, my width and my height for corner A are both 5 feet to that 0 moment center distance, because I've got a height of 10 feet and a width of 10 feet from A to B. I've got my 133 pounds that we found for the shear, and I'm looking for the internal shear AB and the internal normal force AB. Now really all I need is the shear, because my next free body diagram, I'll be taking the section right here to find the magnitude of that moment to the right of A for my moment diagram. Because I'm just drawing the moment diagram and all I need is shear AB, if I sum moments about A, that will be a connection point for normal AB and normal AE that I don't need for this particular problem, and all I'm left with is my one unknown, shear AB. Solving for internal shear AB, which is in the middle of girder A to B, I find it's a negative 133.3, which makes sense. It needs to be acting up for compression in the top to draw the moment diagram in my assumed directions up here for my approximate method. So next, I'm going to take a free body diagram of the segment of the girder from A to the center line. So sectioning right here, just to the right of A, I'm going to have my shear that I just solved for, negative 133. My normal AB is still there, and I'm also going to have my AY reaction, my AX reaction, and my moment at A that I've drawn compression in the top because I know it's going to end up there. Solving for moment at A, it's going to equal to 133.3 times 5 feet, which is equal to 667 pound-feet with compression in the top. Coming back to our moment diagram that I've got sketched up here, that means that this is 667. And then down here, just to the left of B, we are also at 667 due to symmetry. Now I need to solve for the moment just to the right of B. Looking at corner B, I've put in my shear at A that we already solved for, negative 133.3. I still have the normal force that I haven't solved for. I have the 266.7, that's the 2V from that first free body diagram. I have the shear BC, which is the only thing that I want because I'm looking for this reaction moment right there at B. And I find that if I sum moments about B, my normal forces are all going to pass through here, which means they have zero distance from my moment equation. Remember that all of these zero moment locations are at half the span. So I've got the 5 feet from A to B, the 5 feet from B to F, and then because the bay is 12 feet from B to C, half of that is 6 feet to that midspan. And I solve for my internal shear BC is equal to 111.1 pounds. I also get a negative value, so it is also acting up. And once again, I'm going to draw a small little segment from to the right of B to that center point to find that internal moment to the right of B. And our moment reaction just to the right of B is going to be the 111.1 times 6 feet, which is 667 pound-feet. The last moment that I need is from C to D, and I think I'm going to take corner D, a little bit smaller free body diagram for me to deal with. Again, summing my moments about D to take care of the normal forces that I don't want to solve for. I have shear DC times 4 feet and the 133.3 times 5. And I find that shear DC is equal to 166.7 pounds, and it is acting down. So I need my last free body diagram just to the left of D to get that internal moment force. And my moment at D is going to equal to 166.7 times 4, which is equal to 667 pound-feet. Finishing out our moment diagram, this is 667, as is this due to symmetry. Now this one worked out that all the numbers are the same, but it doesn't always work out that way.